So thinking more broadly, Eisner suggests, well, another way, and this one might really resonate with computer science educators, but another way is problem-solving objectives. But it's very different than how many people talk about problem solving in computer science. So here's a quote from page 101. Quote, "In the problem solving objective, the students formulate or are given a problem to solve. Say, to find out how deterrence to smoking might be more effective, or how to design a paper structure that will hold 2 bricks 16 inches above a table, or how the variety and quality of food served in the school cafeteria could be increased within the existing budget. In each of these examples, the problem is posed and the criteria that need to be achieved to resolve the problem are fairly clear, but the forms of its solution are virtually infinite." End quote. That is a very important distinction there, as opposed to what is typically taught in like puzzle-based platforms, where there is one correct solution to be able to solve a particular problem. This is instead saying, hey, broadly speaking, we have this problem, and there are an infinite number of ways that we can kind of solve this particular problem. This gets at like what Wiggins and McTighe talks about in their understanding by design framework of like a big idea or an essential question. It is not a specific question, but it is a question that could be explored through many different perspectives and many different solutions to a particular problem. And this does relate to some of the computer science standards like CSTA's national standards. So here's a quote from page 101. Quote, "The point is that the shapes of the solutions, the forms they take, are highly variable. Alternative solutions to problem-solving objectives could be discussed in class so that the students could begin to appreciate the practical costs." End quote. Now think of that in relation to like some of the algorithms and programming standards, where you are to compare or contrast like multiple algorithms. So if we have a problem and the students come up with different algorithms to solve that particular problem, cool. Let's put them both up on the board and let's talk about how they are similar and different. Which one works for different scenarios and which one's better in what ways or worse in what ways and why. But that kind of an idea of comparing and understanding could be done not just at the algorithmic level, but at the broader level of solutions to problems. Not just like comparing line by line, how is this for loop used compared to a while loop, but instead thinking of what kind of thought went into the solution of the problem. So instead of focusing on syntax, we focus on the thought that went behind the project or solution to a problem. And Eisner relates this to like engineers and architects. There are many different ways that an engineer might construct a bridge, or that an architect might create a building. Many different floor plans that can be used, many different materials that can be used. All of these will have different kind of impacts. And what the engineers and the architects know in advance are the problems, not necessarily the solutions. What might be considered an appropriate solution might not be understood until midway through or even towards the end of work on a particular problem. If you're constructing a bridge and you had some assumptions going into mind and you find out, well, that water is not as solid as we think. We need to construct something to stabilize some of the pillars. Or an architect will draw up a floor plan and bring it to the client, and the client might go, yeah, we like this, but what if you can make it an open floor concept? I've been watching HGTV. And they go back to the drawing board and they come up with a new potential solution to that new context that is provided. But then we relate this to scientists, and Eisner points out that scientists are often the ones who are actually coming up with the problems that they're going to investigate. And that gets back to what I was just talking about with rhizomatic learning. So instead of teachers coming into a context and saying to a student, hey, we have a problem, you, the student, are going to solve this. Instead, we can say, hey, student, what kind of problems might you solve? What kind of questions do you have? Where might you explore? This is a very different approach that relates to the rhizomatic approach that's discussed in many other podcast episodes on this podcast. And again, I include links to those in the show notes. This approach, instead of a behavioral objective, quote, places a premium on cognitive flexibility, on intellectual exploration, on the higher mental processes, end quote. It's from page 103.